Hello and good day to you. So today we're looking at outliers with the intent to discuss leverage, residuals and Cooks D. The reason we're looking at this is if you've been following along with the videos, you've got to a point where you should be able to create a nice fitted model. And if you've created a nice fitted model, you then want to look at what are the oddities from that model. You might want to do this for two reasons. One is removing them from your data and rerunning your regression will provide a better model because large outliers have large effects on the regression. And the other reason is to form discussion points with domain experts, customers and managers, because once you've identified what are these outliers, you stand to gain some knowledge by looking into them and looking why they have that effect. So if you want to follow along, you need to bring in the libraries ggplot2 and car. I'm using a Anscombe's quartet to illustrate what I'm talking about, residuals and leverage first. If you want to go back to a previous video about Anscombe's quartet, you can in this series. But in brief, Anscombe's quartet, all these values have the same linear regression. Now, you can think about the residual as the vertical difference between the spot and the regression, but you can also think of leverage as the horizontal difference between the line and the dot. So here you might have to say we've got quite a medium leverage, and over here you might say we've got quite a large leverage. Now when an individual point has both a large leverage and a large residual, we would say it has a large influence, because if we pulled out that single dot, we stand a very high chance of changing that line and causing that line to go lower. If you can imagine, this is a great way of showing it, because that line would go down there. But if I removed any one of these individual dots, it would probably have a much smaller effect of that individual linear regression. Though, to be more mathematically precise, they do have a much more complicated version of leverage and Cooks D, which I'm going to go through later in the video. But if you get your head around that at the starting point, it makes it very easy to think about the rest of it. Now, if you're following along, please go to Kaggle and look for this real estate data, which we've used many times before. I'm going to create a model, which I am then going to look into, and some explanation on. I've created a model for house price. I'm using a house age and distance to the nearest MRT station and a number of convenience stores as a predictive model. If I'm to plot that model as I showed previously, you will get a series of charts on the residual. Now, you can probably already spot the likely candidates for outliers, but one of the strengths of Cooks distance is it gives a very mathematical way of defining what an outlier should look like. So what they tend to say is anything above 1 in Cooks distance, which you can see nicely plotted out here, should be removed. You can see that it's got some numbers, they'll correlate to this number here. To give you an idea of some of the outliers it might be looking at. You've got your standardized residuals and your leverage down here, and you can think of that as, as stuff goes up like this, it's got more influence, and therefore the Cooks D increases. To explain Cooks D in more mathematical terms, it's defined as a regression with and without the individual value you're testing to get a estimate. So each value here has a Cooks D, and what we do is compute the difference squared between the regression with and without. So mathematically you're creating a linear regression line as you would do using the matrix calculations. And then having got that difference and squared, you're going to divide by the mean squared error multiplied by 2 of the whole population. And I'm sure you're not going to remember that, which is why it's easier to think of Cooks D as a really good rule of thumb measure of influence, and think of it the term I just gave you of high residual, high leverage, and by it being this high measure of influence, it can hopefully give you an idea of what's important to remove. I'll go on into some more detail about that in a sec. To define leverage more formally, you assume that everything's normalized and standardized around 0. You square your standardized value, add 1 and divide by n. Though it correlates so closely to your value as your vertical value that you can think of it like that as a rule of thumb. But you can, if you're ever wondering why these distances aren't normalized and standardized to your values you're looking at, that's the reason, because leverage is its own little calculation when done properly. Now, formal definition of outliers is, there's several. They sort of say if the Cooks D is 3 times mean, or 4 divided by n, when n is the number of observations you're looking at, or any value over 1, you should start to think whether it's an outlier. So that gives you one way of looking into your data. You can start with you can start by building a model, doing a plot, and looking at and going through the 4 different plots. Get to the last one, and there's your residuals and leverage, and you've got your Cooks D1. You can go into more detail, which is something I love about R. If you want to do a formal hypothesis test, you can do outlier test model with the p-value showing where you've got values that you think you should remove. So you've got your p-value there. And remember, this is a hypothesis test for if this individual line in your data is an outlier, rather than the hypothesis test discussed previously. The underlying test is called the Bonferoni hypothesis test. That is its own interesting thing, which I haven't got time to go into. But unfortunately, you can't do everything in an individual video. So what I'm going to do now is I'm going to show you a really neat way of identifying individual outliers. So I'm doing a sort. As you can see, you can pull out the Cooks distance using this wraparound, this function. You can create a data set. And this is doing the maths for you. And if you do that, this is actually doing the maths we need to look into. Plot the data, and you can visually see which 3 individuals we want to remove based on that calculation. So as you can see, we're using that method of 4 divided by n, when n is the number of rows in the data. And you can see that's produced what we want to remove. And a quick way to remove from your data would be data, open square brackets, minus c, and put in any of the numbers or values you want to remove. we've done that and rerun the model, redo a plot, and if we see now, we've moved, you can't even see the Cooks distance because it's so far off. Now what's that useful for? Well, if you've built a model to forecast something in the future, it's good to be scientific about what is an outlier. It's good to be able to say, this is so wrong and this is so different from everything else that's going on that we do not think it's explicable by the current model, or even to give, you could, as you see, you can bring out the Cooks distance of a model and get it out as a set of data to look into it. Well, I suggest to you that's a great way of being able to quantify and measure in simple ways whether, given your current model, is this thing that you're talking about, is this individual, I don't know, like if you've built a model to, say, predict shoe sales, do you want to be able to see what a really strange day looks like? You want to be able to say, that day was inexplicable, that day just should not have been, or to be able to go to your manager and staff and your customer and go, actually, that was within norms. That might look bizarre, but it's predicted by the model. Yes, the residual was large, but the leverage wasn't huge. It's not going to pull everything out of whack. So you've got two strengths here. One is the ability to, as we did previously, remove the data, which is having an outsized effect on your linear regression, to improve your linear regression model. And the other side is, as a formal way of, once you've got a model, once you've got something that's explaining behaviours, it is one way of quantifying how outlandish something is. You've got both the residual, and you've got both the leverage, and you've got a combined measure of influence in Cooks D. And if you can say, yeah, the residual was high, but the leverage wasn't huge, and sometimes you can then maybe fight back and say, well, that's not as big a deal as you might think it is. But other times you can say, yeah, I really think that was just bizarre what happened there, and I need to look into it some more. And I think that's the real strength of having a proper fitted model for your data like this, that you can identify oddity. So with that, I hope you have a good day and a good night. Have a good one. Speak soon. Bye.